Testing, testing. Hello, hello. Let's go ahead and get started. Okay. I think I can do it like this. It's not too distracting. Okay. Let me... maybe adjust the volume of this a little bit. Okay. Alright, that's where I left off. Let's see. Search to ensure valid index. Okay, let me see this real quick. Min element. Return to the minimum element. Yep. Bubble up process. Bubble down process. I think I was looking at the bubble down. Yeah. Okay, certain index is greater than... left child, right child. Okay. Child, this will be... okay. Set the value of left child to the element at the index, if valid, or else make it infinity. Interesting. They wrote it all kind of in one line like that, right? That's so interesting. They kind of wrote it like... wait, what a... dang, that's... I've never even seen this before. Like, what? You can write it like that? Wait, so... I didn't even know you could write it like that, bro. Shorthand conditional expression, also known as a ternary conditional operator. Ternary. Else B. Okay, so min, the nested if. So min is equals A is minimum. If A is less than B. Wait a minute, so what was wrong with my previous statement then? Hold up. So really I can say if x is less than y, else it equals y is less than x. I can't do else. Okay. Wait. Else. So that should work. Something like that. Interesting. Very interesting. Okay. Okay. Self-age left child index. Self-index bubble down assert index is greater than child index equals 10 times the regular index plus 1 equals self-age left. Right. Right. I get that now. My screen is going crazy right now. There we go. Crazy on me. Okay. So min child, so we're doing a return here. If the value of the index is less than or equal to the minimum two children, nothing. Right, okay. Okay. So. Def insert self. Let me see what we got going here. So it wants me to write an insertion method and a delete minimum method. insert. Let me check why. What do I need? Okay, so somehow this is it. I don't know how. There it is, right there. A pinned element. What? It like already knew, bro. It's supposed to be element. And if we have H and we append the element to the end of the list, self bubble up length of self H minus 1. But it says self dot size though, which is this. Yeah, so can I just do size? Like this should be still like does the same thing, doesn't it? Look at this, bro. Yeah, this should definitely be. Size. So they got the minimum element. Man, I'm confused, man. I'm confused, man. All right. going on with my book, man? Oh my goodness, man. That's so frustrating. Like, I don't understand, man. Where is it? It's right here. Genuinely don't understand. Insert new element into data structure. Delete existing element from data structure. I mean, that's not hard to comprehend. But move this out of the way. This part is like, I don't know where to begin with it. At a loss.
Hello, and in this lecture, I wanted to talk to a little bit about this notion of average case complexity and recurrence relation.
Okay, let's just move on then.
Relations. But before I do that, I also wanted to address the broader question of randomization, which is the theme of this week in algorithms and data structures. Okay, so maybe the title should be randomization in algorithms and data structures, and a couple of technical mentions for average case complexity and recurrence relations. All right. So let us talk more about these topics. All right. So far, when we have looked at running time of algorithms from week one, we started looking at the worst case running time as the worst possible input that someone could actually craft, and what is the running time of that. So here is an example of a function. It's not worth reading. It's just an arbitrary function. But the thing is, it takes in an array A of length n, and it iterates through this array in a couple of nested for loops I and j. Here is like an early exit condition which can happen early. Okay, but in the worst case, this branch of the if then else condition is never taken, you always take this branch. So you can always craft an array in the worst case that can take this branch. And by now, you should be able to argue that this loop's running time is upper bounded by O n squared, where n is the length of the array, and it's actually lower bounded in the worst case by omega n squared.
Hold on, could I like find, let me think here, like Python heaps insertion. Yeah, I see heap sort. This isn't C, I think.
Because I can always craft an input for every n. I can always craft an input which will always not take this branch but always take this branch and result in running time that's proportional to n squared. Combining, we get theta n squared. So I hope this is all clear so far. But this is the worst case running time of algorithms. Now, let's talk about algorithms that use randomness. So here is an example of an algorithm, quote unquote algorithm, or just a function that uses randomness. And what is randomness here? So the idea here is we are defining a function called geometric of p that's going to generate a geometric random variable with parameter p. What's a geometric random variable? Well, think of p as the probability that a coin that you toss turns up heads. So let's say there is a coin you toss and p is the probability it turns up heads. Likewise, 1 minus p is the probability that when you toss the coin it turns up tails. So imagine such a coin is given to you. And what I am doing here is I keep flipping the coin as long as it turns up heads. I keep flipping the coin as long as it turns up heads. But the moment it turns up tails, I stop my experiment and I simply count starting from 0 how many flips I have made. Okay, so in this case, I made this is 1, 2, 3, 4. Okay, so so what you would say is I made 4 flips before I hit a tails, and that's the value returned by this program. And the idea here is we use a statement called flip of p, which is in a random number generator. In this case, with probability p, this will generate a value true, and with probability 1 minus p, it will generate a value false, and interpret true as heads and false as tails. So if I get true, then it's 1 plus. Well, recursively just run the same process again as if nothing happened, just run it again. All right. On the other hand, if it's false, then just return 1. All right. So this is the tails case and the heads case. It's for sure a weird way of writing such a program, but it's a valid program to generate a random number generator. And by the way, Python has a library called random which generates random numbers. Okay, so Python has an ability to generate random numbers, and you can use random.random less than or equal to p as an implementation of flip p. So this is possible to implement in Python. You don't directly have a function called flip, but you can always use inbuilt functions in Python to help you generate something like this. Now the question is, what's in the worst case the running time of this function? And what you would see here is that the worst case, you could argue it's infinity, because you could always be flipping a coin and you could always be returning true. And since you're always returning true, you're always stuck in what seems like an infinite loop. You're constantly just calling geometric p back. And in the worst case, the running time you can say is infinity, because in the worst case, the coin is being controlled by a worst enemy. So your worst enemy is controlling the coin, and therefore you're not going to terminate. So you could say in the worst case, this is non-terminating, and its running time is infinity. But is that really true, right? Is that really true? Now, if you assume that your coin is truly random, now, of course, you are not going to imagine the worst case. What you really want is some kind of an average case. Like on the average, how fast does this algorithm run? How many steps, how many calls to geometric does it make before it terminates? All right. So now let's ask this question of why randomness. And uh, we can split this into two broad categories, and there are other categories, but let's flip this into two broad categories. So, in one category, the reason we study randomness is you have an algorithm, okay, you have implemented an algorithm, and you have all possible inputs, let's say of some size, okay, and this could be an infinite set of inputs. All right. And worst case analysis, remember, is always going after the worst possible input. Okay. An input that's being designed by a special adversary who knows your algorithm and is trying to make you look bad by making the algorithm run for a really, really long time. Right. So you want to make the algorithm run for a really, really long time before it finishes with an answer. And you find that worst case input, and that gives you the big O upper bound and the big so you get the worst case complexity anyway. Now, if you don't want that, right? So in many situations, you're not interested in the worst case because let's say you don't expect that kind of input to be always produced. Maybe inputs come from a truly random source. So maybe there is randomness. Maybe there is randomness in the inputs that an algorithm encounters. And therefore, I want to check what's the average. What does the average inputs running time look like? Okay, and there are algorithms which we will see in this week, and there is a special algorithm called quicksort. There's a special algorithm called quicksort where you will see that the difference between the worst case and the average case is actually fairly substantial. Okay, so you will see that in the worst case, quicksort runs in n squared time, whereas in average case, it runs in n log n time. So average case on the average input, it runs in n log n in the worst case. And there are some algorithms, like there is a famous algorithm called the simplex algorithm for solving linear programs, where the worst case is more like 2 to the power n, whereas the average case is more like n to the power 3. Okay, and this is a big, big, big difference between the worst possible input and the average, how the algorithm behaves on the average. So it's sometimes worth looking at the input of an algorithm as being random. Another paradigm is algorithms that actually inside them have ability to synthesize random numbers, so generate random numbers. So for example, imagine an algorithm that from time to time rolls a die, and based on the outcome of this dice, it's, let's assume it's a truly random dice. Based on calls to this truly random dice, it makes decisions as it runs. So we will see an example again, quicksort, a randomized version, where inside the algorithm you're doing some randomization. And why would you want to do this randomization? Again, it's the same problem. You have various inputs, and it may be the case that the adversary is able to know how your algorithm works intimately and craft a worst case input. But if internally your algorithm randomizes, then it's possible that it balances out um, each input. So what happens then is your algorithm will have different ways of computing the output based on the outcome of the die, and some of these are going to be short, some of these are going to be efficient, and sometimes when you get unlucky it's going to take a long amount of time, but it's going to be what we would in somewhat think of as an equal opportunity offender. So for each input you would have some probability that you get unlucky, and it's hopefully a low probability that you get unlucky and you choose the worst possible path, but you might have a reasonable probability that you are choosing on the average some good path. So this is one reason we use randomness, which is we make the adversary unable to choose one input which is going to be bad for the algorithm. But the price you pay for it is you have to introduce randomness in the algorithm, and as a result of that, some of the executions of the algorithm could take longer than the other executions. So the worst case is going to continue to be uniformly bad, but the average case is going to become good, and which is why we are interested in the average case. All right. My drawing abilities suck, but I hope you are able to appreciate why.
All right, man. It's a lot, dude. I can't even deal with it right now. I just need to take some time. Need to take some time and recalibrate.